So we show the Deutsch algorithm. So maybe what I could do is just refresh this again because we'll look at the code. Okay, just refresh this. So you have a 1-bit function. So there are 4 possibilities, right? So you can map the x 0, 1 to these 4 possibilities, right? 0, 0, 1, 1, 1, 0, 0, 1. I group into these two, red and blue. This is constant, and this is balance. Basically, that doesn't matter what the input is, always output the same value. And balance is you have the same number of 1 and 0. Okay. This can be generated to more qubits, but this is probably the first quantum algorithm. It came up by David Deutsch. So the solution, okay, classically, if you want to answer this question, you need to evaluate both values, 0 and 1. Quantum mechanically, you can actually do it once. So I'm not going to go to the detail. The idea is that you input the register instead of just 0 or 1, you enter as a superposition 0 minus 1, the second register. This one using 0 plus 1. By the analysis that we provided in the actually last course, quantification, use phase kickback, you can analyze. So these are all in the slides that I already uploaded. If you measure to be plus, this will be a constant. This means that this circuit that implemented function f will be a constant. If you get minus, then this is balance. Okay, and this is the circuit. This is that you all will assume that it start with 0, and you do the Hadamard to get a plus, and you have a x to flip to 1 and Hadamard to become minus. Right? To measure in the x minus basis, you use Hadamard. Right, and because quantum computer, some IBM, some measurement is only 0, 1. Okay, if you get 0, it's constant, 1 is balance. Okay, and we talk about how to implement this functions. For example, this is to implement this f4 here, 0 and 1, right? If x is 0, the output is 0. If it's 1, it's 1. And this is actually using CNA to implement that. So if it's 0, this is still 0. If this is 1, if this is 1, then because control NOT will copy that 1 to the second register. So this is F4. You could do this. Okay. And let's take a look of using the Qiskit. I already uploaded it maybe in the notebook for last week. You can download. Um, so everyone download the code already. Let me just see where. It's not like that. The code is in bright space. It's showing where the code is. I can.
I may not be here.
Who can find where the code is? Raise your hand if you know where to find. Tell the person who next to you who.
Okay. Are these the notebooks for today that you referred?
But we do the notebook for the we do the Deutsch first, and then there will be more codes.
Starting with Deutsch from
Yeah.
29.
Yeah, 29.
Okay.
Need to be able to share this Deutsch. Okay, it's here. So what we're going to do is we'll not print out the circuit, because if you see the circuit, you know what the function is. This is just for the programming. We're going to hide this, and so we're going to write the oracle. So oracle basically just a function, a random function, 0 and 1. It's just a list. Okay, the first will be the F0, the second will be F1, but will be just run this, and we're not going to see that. Okay, and for Qiskit, we'll explain more, but the basic is you import quantum circuit. They need to also quantum register or classical register if you want to use the classical output. If you have any question, just raise your hand. Okay. Yeah. So maybe yeah, just to show you again, it's here. Okay, I just register you, so you show up here. Yeah.
You just send all of those.
Okay. Okay, good. But it's in the content.
I'll
Yeah.
find it.
Just for everyone else, it's in the content. Yeah, because already distribute the notebook for the Deutsch already. Okay. So we're here. See, I have open many IBM tab. So the oracle would be something that add the value to the second register, and we're using the control node. Remember, if the secret, so there are 4 possibilities, and as in the notebook or in the slide, this is actually in the homework. If you remember the homework, there was a homework about how do you implement right f function last semester. So this is an example of this f4. Okay, but we go back here maybe. Right, you implement f4 using this one, using C0. Basically, this UF is this C0, right? You can see that, right? Because if this is 0, this doesn't do anything on this qubit. If it's 1, then it flip. So basically, it's add 1 to here. And this one, F3, is really just inverting that. So at the end, you have an X here, right? Minimize this. Okay. Oh, that's this here, right? And the first two is easier, right? The first two is that if it's F1, like 0, 0, you do nothing. The first is you put nothing here. I don't know, it responds to my lecture. And 1, 1 is and 1, 1 is just this is nothing, identity. And this is just X in the second register. This is C naught with X, and this is C naught, right? You could also do that, but the one thing you also need to flip this because you don't want to change the first register. You don't want to change the first register, right? This is like the first register has remained the same. Yeah. So if you flip that, you need to flip back. So you need to have 2x. Okay. So we basically need to implement these 4 possibilities. And this is done by these 2 options, right? This is basically F0. And if F0 is 1, as we see in the 1, 1 case, actually, no, this secret function, yeah, if this is 1, 0, then we will do this. And if it's 0, this will not do. So this will actually the third case, right? And you can check if this is 0, it won't implement this. If it's 1, it will implement C naught, right? And if both are 0, nothing is added. So it's identity. If you have both being 1, you have C naught here and there appear twice. So you are left with X. So I'm just explaining that you get the 4 cases. Okay. Okay. So this is the oracle. So you define this function. So the way you define is you want to return the circuit. Okay, so you define a circuit, it's 2 qubit. I give a name oracle, so it would appear like here it says oracle. So you return this. You can return QC is a circuit, but here I just add a few one more thing is to instruction. I turn this circuit into an instruction. So when I define the Deutsch circuit, this is the initialization. So I just add this dash line barrier to indicate this is initialized in the plus. For the 0th register, for the 1 register, I want it to be a minus. You could also use Adama and C. This is circuit identity, right? Gotta add barrier. Now I append the instruction oracle to the 0 and 1 qubit, right? I append this. So this is if you say circuit dot append, then the instruction you have, and this is the qubit you want to apply according to the order 0 and 1. Okay, and this is just measurement. So this is just measurement. The final part is measurement. Okay. Yeah. So what I do here is just really just say I want to call the oracle. I already defined a secret function. It's just a list of 2 objects. And I say I want to have the Deutsch circuit. Can I ignore? And if you use the circuit, this with dot and MPL, this would draw nicely like this. I did not, what is Oracle is not defined. I didn't enter this. Try, you can run the code as you. as you wish. And you can also play with this, right? So we'll talk about the draw function. Okay. But if you may not if you do not install the complete package, you may not be able to show this, but it will print out the error message. So if you use draw, they will use like text way of drawing it. If you have error on the code, you can raise your hand because it's, yeah. Can you get this diagram? Everyone get this diagram? If you not, you may need to install some other packages in Python, like LaTeX and other things. Yeah, but I want to make sure that everyone can do this. If you cannot, just let me know. Because it would output that some package is needed, and you just install that, and then run again. Okay. Okay. And this is a circuit, and we're going to run the simulator to simulate the quantum computer or the circuit. Okay. The simulator we would use is in this air simulator. You need to have installed the Qiskit air package. You need to, if you don't have this, you run this code, if it says error, there's no Qiskit air, then you need to install that, like use PIP or use whatever your Python. Okay, so we'll import the Qiskit air. It's a air simulator. It's a simulator. So I just assigned a simulator. Additionally, I also import transpile function from Qiskit. Transpile is not necessarily needed here because we're using simulator. But if you want to use real device, you need to translate or transpile the circuit into an instruction that the machine understand. Okay. But I do this anyway. So I say transpile my circuit to something that my simulator can understand. Okay, simulator would understand most of these. Okay, and I run. I use simulator.run. Okay, so this would be just running that. So if you want, you could I could break down this into, maybe I could break down this into 2 lines. First, I say job. Sometimes you see people say job run, right? You then just get the job. And if you are on real machine, what you want to do is print out the job ID. Okay, because you notebook may disconnect it, and then you have job ID, you can retrieve it. Of course, there will be a web page that you can check what job you have launched, but simulator does not have a job ID, but useful for real devices. Okay, so you can say this, and then you can say counts equal to, the result will be stored in job, and then you say how to retrieve the count is the job.result, and then you get count. We can also break down into many layers if you want. You could say results equal to, we'll get back that to later. Okay, you can also do this, and for example, you can print what job result is, and counts equal results dot get count. I mean, this is they designed this way, so you have to remember. Okay, so then I'm going to run this. It would, yeah, it will use the simulator, and this is printing out This is not job ID. It's just something, not really a job ID, but this is the result. And this sort of have all the information. Okay. Oh, and then here I say sharp equal to 1024. It's like I repeat this many times. Imagine you have quantum computer, repeat this 1024 times and keep the statistic. Okay. Yeah, and you can print count. And what we did here is basically get count is from this job. You can also say what is this object, right? What exactly is job? Sorry, result. Okay. And what is this? So it's something that they design already in the Qiskit results. Results. It's an object or class or something. I don't know exactly how to frame it. It's Qiskit that result that result that is result. You can go to the documentation. But if you know Python well enough, you could read this and then be able to figure out how to get the information here. Yeah, how to get this information. But for me, I go to the documentation. This is other thing will come. This is the Python we learned as. We can say Google Qiskit result, and it would show the documentation and see what result. So it's a class. Qiskit.result.result. It's a class, and there's a description of this class. Okay, we don't need to worry about too much detail. I just want to show you there are some property you get, for example, job ID or something, and whether it's successful or not. The method is how you get things like data. Method is a function. We reviewed the Python last time. We define class, and as a method is basically a function defined inside a class. There are also dictionary. This dictionary is used to store these count. So let me go back. So my count is this. So remember, I reviewed the Python. This structure is a dictionary. So 0 and is corresponding to the measured result, and 1024. Of course, this is ideal simulator. So we get ideal. Okay, so we can reveal the oracle. Now we can reveal what exactly is oracle. Is this a constant, right? So this is the function we have. The secret function is actually 0. You may get different one. Okay. So this is really a constant. So it's get the correct result. This is using ideal simulator. If you use noisy simulator or use real device, you'll get also 1. Yeah. Okay. Any question on this? Any question? Later we can also discuss how you yeah.
In IBM,
Yeah.
whatever, like your favorites, one of theories, like
Yeah.
what's the typical scale in noise here in terms of the output? That's simple to keep the system. It's like
Yeah.
1%. Like
It depends on, of course, depends on which device and which qubit. For example, the CNOT gate noise is roughly of order 10 to the minus 3 to 10 to the minus 2. The better device can have 10 to the minus 4. And there are also other. So yeah, so we'll cover this, but let me see if I can get.
It's for kernels when you actually run circuit errors at bottom.
Would the refuse come to the queue?
Let me show you. If you register, right? You register IBM, you can go and see their machines. This is this machine called Marrakesh, and you go to this, you see they show you the error. So this is probably the better device among those two. So it can vary. Like this is really bad link, right?
How do they measure this error?
Yeah, so there is a characterization. Yeah, you could. I don't know exactly how they measure, but there are, for example, you can you can use, for example, the so-called randomized benchmarking. There, you just measure how good the gate is. I think they would do the characterization. I don't know exactly in parallel. Like I would probably characterize these 2 qubit and those 2 qubit and just characterizing the CNOT gate, then the 1 qubit gate, etc. We'll talk about those maybe later. And you also see there's a readout error. When you read out is 0 or 1, you cannot trust it 100%. Like there's some error.
We only have zero and the readout. Do they have access there?
They have many errors. They have this T1, T2, relaxation time, decoherence time. There's also other error. There are other. If you scroll down, there are identity RX gate error. This is a rotational axis Z error. You just yeah.
Are they available for us?
This is available for you to see. But in your account, there are like 10 minutes free runtime on some of the machine, maybe 1 or 2, I'm not sure. Yeah. 10 minutes is probably enough to run some simple job. Yeah. For these.
But each job is just millisecond.
Depends. So if I go these are jobs that I ran. For example, on this machine, I use 5 seconds, 4 seconds, 2 seconds. And you need to make sure the code can be run. For example, I have a lot of error failed. A fail, it can be quite subtle. Maybe even if you run simulator, it works. But there are some quite subtle things on real device. So there are these. I try. Yeah, I try. But some can run quite long, like 4 minutes. Some even longer. Some even longer, like 43 minutes. And in a paper that we published 2 years ago, we ran on 100 qubit to realize a spin chain ground state. Each point took an hour. Each point took an hour to get. And then we did 3 or 4 points to extrapolate. So each, for example, XZ model, each value, yeah, costs like 2 hours, more than 2 hours, 3 hours. It's not. I mean, the national lab is paying for that. Yeah.
Why does it blow up like this? It's kind of like scale because it's just.
You mean this?
Because there's so much noise that the statistic is like it's like very washed out. So
What do you mean by blow up? What?
As in like you go from like seconds like.
Oh, you
5
this
minutes,
the
like,
it's different circuit.
I know.
And how many? Yeah. Yeah.
I know it's different circuits.
Different circuit and different many circuits.
What's the main reason like this can like blow up?
It's how many? It's
Double the qubits.
you say how many shots. Yeah.
So
If you want accuracy, you want more shot. Like maybe I run 10K shots. There I run 1K and 10K already 10 times 10. So you can see what's used here.
Basically more qubits, there's more noise. It's harder to actually extract the good estimation of the mean.
You want to have more
Then you have
statistics.
so you need more shots.
You have statistics. You want statistics, right? And sometimes, yeah. Say that again.
Given the of the circuit break?
The depth can increase. Yeah, if you have 10 times the depth, then it's times 10. Yeah.
For each run, I think that you have to still within a second.
Yeah, so yeah, usually it won't take too yeah, so we'll show you how to run on real device, but this is using simulator. Okay. I have too many things open. Okay. Yeah, so this is probably the first notebook, actually the second notebook on Qiskit. Yeah.
Do you need to consider the processor structure? Do you need to do the
Yeah.
compile?
Yeah, so that's why I say there's a transpile. We'll talk about more on that later. Transpile. You need to transpile just to. This is the notebook that we used the first lecture, right? So there's for example, we create this fail state and do some measurement.
Real computer.
This is also using the simulator, but you can do it on real computer. I think. Okay. This is showing the map, like you need to map which qubit you map to, right? So you need to do the transpilation. Okay, I'm just showing, and the observable would also be mapped. Okay, on real backend, this is an example that I did run on real backend. So this backend is called Brisbane, and this is simulator, and this is the real measurement, real. Okay. So if you know how to run simulator, most of the time you probably will be successful on running on the real back end, but the result may not be similar, may not. So for example, here is similar because really small circuit, really short depth. But for other things, I was trying something else. Yeah, so I was trying something else. Okay, but this is quite noisy. I expect you only have the left half. Okay, but this is already the best machine there. So ideally, you would expect something I might have. Yeah, no, this is different. This is the even worse machine, right? It's even you don't see the left and the right, right? This is a different machine. This is really running on those. And these probably take a few seconds. Those are the job. It failed a few times until I was able to make it work. Yeah, but most of the time we will just be happy doing the simulator here. Okay. You can also simulate.
Oh, really?
It's not, I mean, it cannot predict the real outcome. Yeah. The point is to see if the noise obey these noise model, how much worse compared to the ideal. Yeah, you need to get a sense of how bad, even though you cannot predict very well. Yeah. But for a real machine, if it get improved and much better, then the simulator may get good prediction. Okay. Let's get back to the. Okay, get back to the slides. So, well, okay, we did this, and then we'll talk about circuit, and then come back to other simple algorithm. Who remember other simple algorithm? We talk about Deutsch, and we also talk about other algorithms. Well, we'll come back to that. There's some Bernstein, Vasarani, and Simon's algorithm. Of course, Shor's algorithm is more advanced. Okay. Circuit, this is the rough idea of quantum computation. You have gates. It could be multiple qubit gate, but I just show that these are 2 qubits. It could also be 1 qubit, right? So each disk could be just 1 qubit. And generally, this represents general quantum computation. And you don't have to run this way, but you could run simultaneously many gates here, right? So 3-step is you initialize, as we see, right? You initialize, then gate operation, you measurement. All the 3-step can have errors. And there's a notion of universality is any unitary circuit can be decomposed into 1 qubit gate, for example, the Hadamard gate and the T gate, or arbitrary rotation, and 2 qubit gate. You only need one kind of 2 qubit gate, for example, to control NOT. Okay. And in the IBM devices, they not necessarily use control NOT as a native gate. They use other gate. They call it echo cross resonance gate, which is more appropriate to the device. But this can be converted to CNOT by some gate identity. For example, we talk about some universal set of gates, 1 qubit, right? We talk about these in QoS course. Example, universal set of gates could be arbitrary rotation and CNOT. But there's also approximate. If you only have Hadamard T gate, CNOT, then it's sufficient because you can T gate is a non-Clifford gate, then you can actually generate other non-Clifford gate. There's also other. This is not so important. I think important things are these gate identity. You need to know these gate identity. You apply X, and then H is equivalent to H and followed by Z. CNOT gate, this commute with Z, but X, it doesn't commute, so it actually bring X in the second register. Z is the opposite. This is what's used in error correction a lot. The error can propagate. So you don't want error to propagate into too many qubits, things like that. You can also have this identity. If I have control NOT or control X, how do I get control Z? I do the Hadamard, for example. So you can have these transformation. These are really simple. So this example here, swap gate constructed from CNOT. Why do I need this? Because I don't have a swap in the actual device. In order to do swap, I need to use 3 gate to implement the swap. Because if I have 100 qubit circuit, if I want to do the qubit 1 and 100, if they don't have a direct connection, I will need to swap the information and then swap back, which can be costly. Yeah, and also some other control gate. Let's see. You see, we can see a few gates. If you have a notebook, you can open the circuit. This one, circuit basic. Yeah, I try to make the code compatible with the newer Qiskit version, because they change so quickly. Next year, I have to do it again. Okay, so this is adapted from some of their old tutorial. Okay, so Qiskit circuit, you can just play along with this. We already seen this in for circuit. 3 is saying that I want to have a 3 qubit circuit. Okay, and I can print that. I say draw output. You can skip output. In the beginning, there's nothing, right? There's nothing applied. Okay. Then we apply the Hadamard gate. So you need to remember the gate. Hadamard gate is lowercase h. C naught is Cx. 0 is the control qubit. 1 is the target qubit. You can also apply 0 to here. We only have 3 qubits, so 0, 2, or 1 and 2, etc. If you have 100 qubit, you can apply from 0 to 99, but you may not directly run that on the real device. So you need to transpile and try to help you to do the swap if you don't have a direct connection. So that's why you need to have transpilation.
Okay. Do just
Yeah, you need to say I want to transpile. Okay, so this you can also, if you're curious, you can also say what is Turk. What is the type? Right, is this Qiskit circuit dot quantum circuit class, and you can go to the documentation. Okay, I just show you how you can draw this. Just MBL. You need to make sure you install this matplotlib in your Python. Okay, simulator. So we talk about air simulator. It can allow you to simulate the shot like you measure. But sometimes maybe you just want to have the vectors, the output of the state. So here I'm showing you using the state vector. So what you do here, okay, state vector. Here I define a state. It's from integer 0 and then 3 because I have 3 qubits. And I want to simulate the evolution of that circuit. I just use state.evolution, evolve. Okay, and I show what's the state, final state. This is a state vector. If you don't have a LaTeX, then it would just show you. If you don't use vector, it's fine. Even if you don't have that, but you need to install that. Otherwise, it will just show you the array. Okay. It's nice to have LaTeX. So you can also have these visualization. You can import these array to LaTeX. So when you install Qiskit, you need to make sure you also install the visualization. Okay, so array to LaTeX. Yeah, so it will show this. This object from state vector. This is, you can also ask what is this, right? So you can always see. If you want to know more, I mean, I cannot cover everything, so I don't know all of them, but you can. The nice thing is you can always refer to the documentation. The state is defined Qiskit quantum info that state vector that state is a class in this class. Okay. You can ask, and you can go to the documentation to see what property the class has. It has this probability. It's really saying that if you measure 0-1 basis, it's really turned this into probability. And you could also sample counts, like sample the measurement and see what's the count. Right? So it's really similar to what we did this count in simulator, air simulator, right? It shows this 0 as 522, 111, 502. Okay, so that's the state vector. There's also operator, right? Sometimes we want to evaluate some expectation value x here, for example, y, izz. And the way I write here is, so I import the package sparse poly operator. And the way to define operator is, or observable is say, okay, I want to have these poly operator in this form, xxx, y, identity zz, a list, and then another list is the coefficient. So really just 0.2 times xxx plus 0.1 times yyi plus 0.5 times izz. Okay, and then you can say expectation value. So this is that operator evaluated with respect to the state that we define. Okay.
Why is it different for the two? Like the shells are different for the two identities.
The two are different. Yeah, it's a good question. Why? Okay, why do you think they are different?
Did you run that?
This is simulator.
Yeah, it's a simulator. Are you simulating the errors?
So you have 50%. Ideally, it should be 50%. But why you don't get 512, 512 each?
Like square
of n.
要加上 rolling dice,
Yeah, this is the statistics, right?
not
Yeah.
no error, just rolling dice.
Yeah, it's a finite size, exactly. The 1 over square root and deviation. So the simulator is taking that into account. It's not okay saying that it is multiplied the probability and giving you 512, 512. Then that's too ideal, right? I think what it does is really throwing a dice, right? And you use some random number generator. It's greater than 1/2, it's 0, and smaller it's 1. So therefore, you have some statistics. Okay. You can also see the state. This is a Q-sphere. If you remember seeing the quantum composer, they have this Q-sphere. It's not a block sphere because it's representing multiple qubits. Okay, basically 3 0 and 3 1. So these are the two components. So they just draw a line.
Other places on the
So there are these two planes that has one bit flip from that. So it will be 0 0 1, 1 0 1 0, and 1 0 0, and it is two flip. Yeah. You can also draw these. We don't usually use these very often. Rington. There's density metric has a real part and imaginary part. Maybe this is used more often using these state city. So like using these bars. Experimentalists use these quite a lot. You can plot the block sphere. Because this is a GZ state, it just plot the reduced density metric of each one. It's identity, right? So identity times 1/2 is at the center. So there's nothing here. Okay. So there's also operator. So I have defined a circuit, right? Circuit is you can turn it into instruction, like apply these gate. So it's a unitary. So you can also see it's unitary matrix. So you say operator input the circuit to that, you can output this. Okay, so this is a unitary. Of course, if you want to, in a nice form that you say data, okay, this U data will show that, but you say U dot draw, then we'll draw this nice form.
When you draw the blocks there, are you tracing out the other?
Yeah. If block sphere is for 1 qubit, so it's tracing out the other. Okay. We have seen something similar like this. Okay, but this we haven't explicitly. So we define a circuit here. 3 is 3 qubit. The second argument 3 is 3 classical bit. And here I add barrier. Okay, so this is not for visualization. I don't know. So this is measurement. It defined a measurement. This define a second circuit, right? We have the circuit. Its name is circ, right? We have circ previously, right? We have circ previously. It's creating the GZ state. Here is showing you a different way. Okay, you define a circuit which only deal with measurement. So 3 qubits, 3 classical bits, and it draw the barrier here and measure all the 3 qubit and record the result to the 3 corresponding bits. Okay. So here is showing a feature that you have a circuit 1, you can actually compose that. So if you say QC equal to this measurement circuit, compose circ, then you put the 2 circuit together. It's just a feature that they developed. So you can put this measurement circuit to the end of the GSZ circuit, so you can do the measurement. What I could do is, for example, I show this measurement circuit. Okay, you could play with the code yourself. I print this as compose circuit.
Either parentheses after display.
What's that?
Or with display. Right.
Oh yeah. Okay, so this is the measurement circuit, and this is the compose circuit. I don't need to go over everything, but this is
What is the component?
compose is add this.
Oh,
Okay. You just need to see the action. So the name is the name, okay? So we talk about the transpile, right? You need to be able to let the machines or simulator or they call these back ends to understand, okay? So here we use the air simulator we did before, and we could, there's not much difference. So let me first say print original circuit. And this is the transpile circuit. In this case will be the same. It's never close. The same thing. This original and the transpile circuit. It's doing some translation, but it's because the simulator can simulate all the circuit, but there will be difference in the real machine. Okay, and we also see this run, backend.run, but I want to point out when you use this backend.run, it will soon be removed. So we'll not be able to use this feature to run the job, but we'll talk about how you run. Okay, and we already see this. Okay, sometimes the notebook or the codes would have things that you learned before and repeat it. It's probably okay. And you see more times than you get used to that. Here I import this visualization tool, plot histogram. So I can just say plot histogram and plot the counts. And this is useful. Okay, so there's also other simulators. So let me not go over that. This is basic simulator. You can run the code. It basically does the same thing. There's some difference between the two. Maybe one is more efficient because the way that it was implemented. Yeah, maybe basic simulator was the first, and they have improved this air simulator. Okay. This above was the original circuit. I added material on quantum Fourier transform, but it's really just for now. You just it's a additional circuit that implement that. So to load that, you go from this library. From Qiskit that circuit that library, you import QFT is quantum Fourier transform, and just show you the circuit. I have 3 qubit, and right. So I have 3 qubit. So the way to use that, you append the quantum Fourier transform with 3 qubit, and this is the range you want. You may apply quantum Fourier transform. This range is 0, 1, 2. You may change a different way, like 0, 2, 1, then it would apply in a different order. Okay, and then I say measure all. Okay, this is additional material, and I do the translation here. It's not necessary because the simulator, but real device. So for real device, if you do translation, you will see that these kind of circuit, it get decomposed into the basic circuit on the machine.
Do they do optimization?
You can do optimization.
So they won't automatically do.
No, you have to say what kind of level optimization. Okay, so this is that. Did it run this?
It's more than just like transforming to the universal bits and
There are also some optimization because you don't want the circuit depth to be too large. Okay, so that's the first notebook. If you want to learn more about the plotting function, this is the second notebook. Basically from visualization. So I'm not going to go over everything. So we know the histogram, right? You can count, you can plot histogram. So I'm just quickly let you see what's there. And you can play cell. So if you have 2 results, you can actually plot together, like using the list. And you can also add legend. Like here, we didn't add any legend. You can add legend, the first and the second, etc. Right around this. You could also different colors. So it may be useful when you are publishing paper. You want to make it nice. So some practical benefit of learning these. Okay, there are other plotting stuff. Let me see if anything. useful. Here, this is the draw the circuit. And here is plot the city. We already saw that. So let me go over and then plot sphere. Okay, and can change different color. In the plot circuit, there might be other options which may be useful. This is yeah, we'll probably see that somewhere else. This is blocks of here. You have, if you have a vector, you can plot that. This is what we use in the high school outreach, but for that I wrote a Mathematica, simple Mathematica. Okay. This code doesn't work. It doesn't show the correct version. So this doesn't work. You could say import Qiskit version. At least this one will show you what version was using. Okay, so that's the second one. So these are the tools that we will need. And later when I talk about go through the code, I won't say that you implicitly know those. This may be a useful one, a summary of all the quantum operation. So we have 1 qubit gate, 2 qubit gate. You need to know what these are. And so, for example, this is the gate that they have. They call this U gate. So this is 1 qubit gate. So here we haven't used quantum register before, but you can say you can define Q is a quantum register. You can even give that a name, and you create a quantum circuit using this quantum register. You could also define classical register and give the classical register name, which can be useful when you plot this. And if you give it the circuit a name, and you can apply. So this U is defined there, and so you can apply this circuit to the initial state, right? But this is just to illustrate that this gate, if you want to draw it nicely, you use MPL. Okay, and we already see this. You can use operator to see the operation. You could, of course, you could also plot that with LaTeX. I mean, I think the way to learn is really just play with this. And the more you do, the more you remember. If you forget, these notebook serve as reference. You go back to see, okay, I remember I know how to do that in that notebook. Go back and read that. That's also useful for myself. So collecting these. P is phase. Yeah, P is a phase gate. Yeah, we just need to, you need to know this, okay, I want to apply a phase gate. What is the name of phase gate? This is basically, this is the summary. Okay. Identity gate is just ID. Okay. Poly gate, X, Y, Z, really standard. Right? So really X apply on which qubit, right? This qubit, the argument of Q can be an integer labeling which qubit, could also be the quantum register, and then say which quantum register. C gate, Clifford gate, including Hadamard. Hadamard is lowercase h. Okay, here you could also have, here I throw in this density matrix. You can also print out the density matrix of a state. So let me not run that. You have the S gate. S gate is this one I. It's also the phase gate with pi over 2 argument. There's S is not Hermitian, so the inverse is S dagger. Okay, S dagger is SDG. SDG.
Oh, other.
There's also T gate. This is the non-Clifford gate. T gate, and there's also a stagger. It's called TDG. So you just need to remember this. There's a rotation route X, Y, Z axis. This is this. Really basic. Is e to the minus I theta, the polymetric over 2. That's the rotation. Okay, so let me not go Y, right? And Z, RX, RY, RZ, multiple qubit. Okay, I want to mention IBM label in a way that this 0 is usually in the textbook when we write 1, 0, 1 will be the first qubit, 0 will be the second qubit, but IBM has a convention, they reverse that. You need to remember this convention. 0 is the least significant, but they draw 0 and then 1. So they read from right to left. It's a convention. Okay. So for example, when you see C naught, in our lecture, we will see it's in terms of 4 by 4, it's 1, 1, and then there's a block of 0, 1, 1, 0. This is for qubit 0 and qubit 1, but for them, it's reversed. So you need to, but the labeling is still 0, 0, 0, 1, 1, 0. So it will be here. That block will be here. It's really a convention. Okay. So here, right? So this is what I said. So this is using this 0 as a control. This is a target. But if you see the matrix operator form, its block is different because the convention is different. It's as if we were doing the second qubit as a control, first qubit target in our old convention. Like so, this block is here. This block is here. Okay, so this knot is here, and this identity is here. Okay. This is a convention you need to remember. Okay, there's also control Y. You can convert control X to control Y by unitary on the second qubit. There's a control Hadamard. We don't use that much, control Hadamard. We seldom use control Hadamard. They also offer the control rotation. Control rotation. Use first qubit as control, and then you rotate if it's 1 on the first qubit. Okay, so for them, sometimes I would call the zeros qubit, sometimes goes first qubit. So it depends on the context. They label because Python label start from 0. Okay. So unitary swap gate, you could say swap, but the implementation, as we saw, would be 3 qubits, 3 C0. And there's other gate, like Toffoli gate. Toffoli gate. This is this matrix is control not. There's also so-called Fredkin gate is control swap. It's control swap. We don't need to use all the gates here. So there's also, as long as you remember the basic gate, 1 qubit, 2 qubit measurement, you just say measure this qubit Q, and you want to put a result in register C. Okay. So we have seen this. You could also reset a qubit. Reset will be set it to 0 state. Sometimes may be useful to reset because you may want to reduce the error of state preparation. Okay. Control operation, this is useful because you can do the measurement and dependent outcome and do the conditional gate. This is introduced as CIF here. I'm going to apply control. I'm going to apply a classically controlled gate to apply to qubit 0 if the C is okay, then C is not defined. I need to start from here. Okay, C was defined much earlier. Here. Qubit. This is useful in terms of recent development. This mixed circuit measurement allow you to more efficiently to achieve some state preparation or some gate operation. The problem here is this CIF is deprecated and we removed. But I will tell you what's the new stuff. Okay. So this is if the register 0 is something, then I apply this qubit. So this C, okay, if it's 0, then I do something, and that 0 can come from the previous measurement. It's another result example. Okay. I didn't define. No, I didn't define the backend. So it's okay. Yeah, so you can have more complicated. Right. So newer thing, I added the newer thing is here. The new thing that definitely is going to work is this if test. And then, for example, lift, you can't ignore the lift for the moment. You can say with QC.if test some C register, and then you do the X gate. Yeah. So for example, this could be okay. I need to go. So it'll be this if test C register. Sometimes they use this C0, C1. If C is 1, then I do the following action. Okay. There's also additional thing, arbitrary state initialization, which we probably will use that in the teleportation, maybe, yeah, homework. Okay, so that's really a quick run through of these notebook, but you can play with these. These are the really basic tool, and assume that you know these gates, functions. Yeah. Okay.
What we are doing on Wednesday?
I'll let you know. Okay. Yeah. So Wednesday, I don't know. Wednesday we'll talk about review some of these, and then basic algorithm. I will upload 2 other basic algorithm. Okay.